This summer, I worked on the directed assembly of binary magnetic particles under Dr. Torres Diaz. A little bit of background. The problem that we encountered is that there is no closed-form expression to quantify the pair interactions between magnetic particles with arbitrary shape. The point dipole approximation is what is currently used to quantify such interactions, but previous research has found that this breaks down with aspect ratios of greater than 1.4. Some possible applications of this research include the production of biological structures of desired size and shape, production of materials with desired electronic, optical, elastic, or other properties, targeted drug delivery by inducing highly localized phase transformations, semiconductors, and biomimetic devices. This is the expression that we came up to quantify the energy of our binary system. We went through and we found the energy of particle of the system with particle J at a variety of different positions, whether it be here, 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 or at any other position around particle I. This is what the energy landscape looks like. What we can tell from this is the energy of the two-particle system with particle J being at any point around particle I, based on the color of that specific point. Higher energies means that the particle is less likely to end up there, while lower energies mean that the particle is more likely to end up there. So in this case, the particle J is more likely to end up on either end of particle I with their dipoles aligning. This is backed up by current research on spheres. This is a sampling of some of the other cases that we tested. We started with smaller aspect ratios such as spheres, before moving on to bigger ones still involving spheres, before we just moved on to aspect ratios of 10 and large, of up to 10. We also tried an arrangement of different angles of particle J with respect to the major axis of particle I. We also looked at the effect of beta on the interaction energy. And we found that, as you can see based on this equation, it is just a prefactor. So the energy minimums stay the same no matter what the beta is. However, the total energy of the system is much greater at higher betas. Based on the energy landscape, we also made a combined energy landscape, which shows the energy of the two-particle system at any position along the surface of particle I and of any orientation of particle J. Here you can see how the points on the individual energy landscapes correspond to points on the combined energy landscape. And what we can tell based on this combined energy landscape is for given two particles with two specific aspect ratios, we can tell what is the most likely orientation of particle J and what is the most likely location that particle J is going to settle at. Here we have a couple different combined energy landscapes, all with the center particle, particle I, having an aspect ratio of 1 or being a sphere. And as you can see, going left to right, as the aspect ratio of particle J increases, the equilibrium configuration becomes more specific as we go from having this large region of blue to these smaller circles of dark blue. And this trend holds up for larger aspect ratios as well. Here we have the particle I having an aspect ratio of 2.51, and as the aspect ratio of particle J increases, we again go from these large areas of blue to these smaller regions of blue before it becomes just tiny ovals again. We thought that this previous trend was due in part because of large differences between the aspect ratios of the two particles. Here we looked at systems in which the particles had the same aspect ratio, and we see that this trend still does hold up, even if it is not as obvious as in previous slides. Here we found that we could invert our energy landscape to get probability. As you can see on the left, there is a very low energy at a theta ij of 180 degrees and a nu of about 90. On the figure on the right, you can see at that same location, there's a dark red circle, which indicates high probability. We looked at the effects that beta has on the probability. Earlier we found that it does not affect the location of the equilibrium configuration. But as seen here, at low betas, there is a very high probability of almost any configuration forming, but at higher betas, that configuration becomes a lot more specific. We also considered the effects that having a magnetic field would have on the configuration. On the figure on the far left without a field, you can see that the lowest energy is at a theta ij of about 180 degrees. At a low alpha 5, you can see that the lowest energy is now at 45 degrees and lower. And on the figure on the far right, you can see that alpha has now dominated the interaction, and there are layers of energy based on how close the particles are to aligning with the field. To conclude, we developed a model to quantify the energy landscape of magnetic ellipsoids with different size and shape at any relative position and orientation. The model that we have matches the current point dipole model for spheres. The interaction parameter beta controls the self-assembled equilibrium configurations. Higher aspect ratios tend to have more specific configurations than low aspect ratios, and the particle field interaction parameter alpha allows tunable configurations in directed assembly. Some further work that could be done on this includes changing the direction of the dipole, which is an additional variable that we did not explore as much. In this case, we could change the direction of the dipole from being oriented along the positive x-axis to being oriented along the y-axis or even the z-axis. The direction that we're currently going right now involves systems with more than 2 particles. In the figure shown, we have about 32 particles with 2 different sizes, and we're looking at how beta and alpha are going to affect the configurations in larger systems.